Alright, welcome everyone to my presentation on novel approach to non-adiabatic transitions in quantum systems. I'm Sean from the University of Warwick, and let's get started. So suppose we have an electron. Now quantum mechanics has a couple of interesting things to say about this electron. Firstly, it can only occupy discrete energy levels. So this right here is known as an energy level diagram. We've effectively got a ladder here. Each rung of this ladder represents an allowed value of energy. So an electron is allowed to have this value of energy, but nothing in between. Okay, and this right here is a hydrogen atom, for instance. Okay, so this is quite different from classical mechanics, right? If you have a regular ball and you throw it, well, it can have a certain range of kinetic energy. But here we're saying that an electron can only have this much, but nothing in between. And another stark contrast with everyday life in classical physics is that if you were to make a measurement of energy, there is no way for you to predict beforehand which energy level you will find the electron in. The best you can do is talk in terms of probabilities. The best you can do is to say that there is this much chance of finding the electron in this state, this much chance, and so on and so forth. So in my project, we focus on two energy levels. Okay? So previous example, we had infinitely many, just focus on two, that'll do. Say I put my electron in the upper energy level, okay, at the beginning of the universe, say, right? So t equals minus infinity, right? Now there's a pretty important result in quantum mechanics called the adiabatic theorem, which states that provided the total energy of your system doesn't change in time, okay? So for instance, if the energy levels right here, if they don't change in time, then if your electron is in one of the energy levels, then it will remain in that energy level forever. So no transitions would happen and life would be pretty boring. However, this is no longer the case if you make your energy levels change in time. So suppose at t equals 0, at the middle of our experiment, we make our energy levels wobble around a little bit. Okay? Then the wobbling dies down. Well, there's going to be a small but non-zero probability that the electron would actually jump down. That's what the adiabatic theorem says. Okay? We can represent the extent of this wobbling by a positive number epsilon. Okay? So my project asks, how does this probability depend on epsilon? Now, the smaller the epsilon is, the smaller the wobbling you've got, and so the less likely it would be for the electron to jump down. However, let's try and find a more precise relationship and quantitatively figure out what the probability is. So in classical mechanics, i.e. everyday life, you've got n particles, and the state of the system of n particles can be simply given by, well, you list the position of each particle at every moment of time, and you also give me the momentum of every particle at each moment of time. And, well, what we traditionally try and do is we try and solve for what the state of a system is. So we know what the forces are that act on each body. We're given some initial conditions, and then we try and solve for the state. So a very simple example might be that you have a ball, right? And you kick it upwards with some initial velocity v naught, and it's under the force of gravity, so mg. And essentially you've got a problem like this. So this is very simple because F is just equal to the weight, right? And it's constant. And this A right here is the acceleration. And so in this case, you'd have a very simple differential equation which you can solve and get the trajectory of the ball. Okay? However, a more useful theoretical approach is, instead of specifying the forces that act on the body, you specify the total energy of the system. So for instance, with this very simple case, you can specify the total energy as the kinetic energy, p squared over 2m, plus some potential energy, which depends on the position. Okay? And this can be modeled, this can be used to model, for instance, a planet orbiting the sun, right, where this is the gravitational potential. Okay, so more theoretically useful approach is to instead give me the total energy, right, the Hamiltonian, and then from that you also give me initial conditions. So you give me the initial position of every particle and its initial momentum or velocity, and I try and solve an equation that's just like Newton's second law to solve for the trajectory. So in this case, this would be Hamilton's equations in one dimension and the partial derivative of the Hamiltonian with respect to position. And this is fairly easy to generalize into 3 dimensions, for instance, and multiple particles. You just look at each component one at a time. Okay, so you try and solve this along with initial conditions given, initial momentum and initial position. Now, what happens in quantum mechanics? So we take a quite different stance. Instead, we're modeling, say, like an electron, and the electron has got certain properties such as energy, momentum, position, spin, etc. Each of these we call observables because you can observe them in an experiment. Now, mathematically, we model each observable as a matrix, right, or more specifically an operator. And this operator is cooked up so that it has eigenvalues which are precisely the possible values that you can observe in an experiment. So for instance, if we go to the Hamiltonian, right, that itself is also an observable, right? You can also observe the total energy of the system. The eigenvalues are plus a half and minus a half, and these are precisely the values of energy that you might measure for your electron, for instance. Okay, now what's very different is that this observable is a random variable. So, like I said beforehand, there is no way for you to predict what the value of energy of your electron would be. The best you can do is talk in terms of probabilities. So formally, what you'd say is you'd ask about what the probability is of finding the energy of the electron to be a half and what the probability is to be minus a half. This is just a random variable. And of course, the same thing applies to any other things you can observe for a quantum system in general. And it's worth noting that operators, so the matrix, are symmetric matrices, or more specifically, they're Hermitian or self-adjoint. Okay? And if you have a matrix that, or an operator which has this property, then you automatically get that the eigenvectors, which correspond to each eigenvalue, form a basis for the vector space that this operator acts on. Okay, and you can get an orthonormal basis of eigenvectors. So instead of listing the position and momentum, just as you do in classical mechanics, you instead represent the state of your system by a wave function. Okay, we'll see that there's actually a more general way of doing this. But this wave function lives inside some vector space. And in fact, this vector space has got a dot product or an inner product associated to it. So in general, this belongs to some Hilbert space. Okay, so a Hilbert space just means it's a vector space with an inner product, and also it's got to be what we call complete. Okay, you can look that up if you want the details. Okay, so let's go to the example of the two-level system because that's what we're interested in, right? The electron can be in the upper energy level or in the lower energy level. So how would we represent this? Well, in this case, our Hilbert space would be C2. Okay, so this is the set of points x, y, where x and y are allowed to be complex numbers. And so a particular configuration of our system, right, particular state of our system is represented by a vector in here, right? Now, what does this all mean for us? Well, like I said, this matrix H is diagonal, okay? or more properly, it's self-adjoint. So that means that it's got an eigenbasis, right? So it's got an eigenvector phi plus and phi minus at each moment of time. And this gives us a basis for C2. So this means that if you give me the state of your system, it's just a vector in C2, so I can write out the components in this basis. And the significance is that these coefficients right here, you can tweak these, right? You can vary these, and each different choices of C1 and C2 give you different choices of this wave function of your state, psi. Okay? This must be obeyed. And, well, the absolute value squared of this guy will tell you how likely you'll be in the upper energy level, and this absolute value squared of this guy will tell you how likely you are to be in the lower energy level. So you want to figure out the state of a system, and if you know the position and momentum of each particle at every moment of time, then you know everything there is to know about your system. The game is that I give you a list of all of the initial conditions, so all of the initial position and initial momentum at this time, and you are given also the Hamiltonian of the system, which is a function of the position, momentum, and time coordinates. And from that, by using Hamilton's equations, right, which is effectively F equals ma, you can determine the state for all time. Okay? So, as a concrete example, think of the planets in our solar system. Right now, if I know exactly where each of the planets are in the solar system, and I know the function which gives me the total energy of this system, then in principle at least, I can determine the future completely precisely. Okay? Now, in stark contrast, quantum mechanics says, hold on a minute, it doesn't make sense to talk about the trajectories of particles. Okay, quantum mechanics says that an electron isn't something with a well-defined position and momentum. Okay? Instead, it's sort of this fuzzy cloud, right? It's sort of somewhere between, a particle and a wave. So instead, all you can know about the configuration of a system, all you can know is the wave function. Okay? So the state of a system is captured by a vector which belongs to some Hilbert space. Okay? Again, Hilbert space just really means a vector space, but you've also got an inner product defined on it, a dot product. Now the game here is that I give you the initial wave function at some time t0, right? And I give you the Hamiltonian, but this time the Hamiltonian is a matrix. Then you use the Schrödinger equation, and if you can solve this, then you can determine the state for all time. And then you can figure out what there is to know about the system. Okay, so let's talk about the mathematics. So let's talk about how you would use the Schrödinger equation to, in principle, solve this problem of figuring out the probability of transitioning. Okay? So this is your wave function, this is your Schrödinger equation, and this epsilon here is that parameter that we talked about. That's to do with the wobbling. And the Hamiltonian is a matrix, and this is sort of the most general you can have for the two-level system. Okay, if the electron can be in one state or in the other. Okay, usually you'd have a row here, but you can argue that you can scale time in such a way to make this equal to a half. Okay, now this Hamiltonian is diagonal, and so it has a bunch of eigenvectors, and the eigenvectors I'll denote by plus a half corresponding plus phi corresponding to the eigenvalue plus a half, and phi minus will be corresponding to the negative eigenvalue. Okay, and so we can talk about what these eigenstates mean. So again, the state of our system is described by a vector in C2. So you can, once you have a basis, then you can describe the system by simply giving the coefficients of the combination of these two bases. Okay, so if you're in an extreme case where the wave function is exactly phi plus, that corresponds to the electron having 100% chance of being in the upper energy level. If your wave function is phi minus instead, then your electron is in the lower energy state. But of course, it's going to be in general a combination of the two. So if your wave function is this, for instance, that would correspond to the electron being in the lower energy state with a probability of 1/2 and in the upper with a probability of 1/2. So, okay, so phi minus and phi plus, they are a basis for C2, okay? And so since this is a vector in C2, okay, when I say C2, it's not this C2 I'm talking about, by the way, it's this, right? So the R2, except we have complex values for the coordinates. So yeah, so as I was saying, generally, if you have a general configuration of this two-level system, it'll be a combination of phi minus and phi plus. And this coefficient right here, this weighting, will be roughly how likely you will find the electron in the lower energy state, and the other one will be how likely it is in the upper energy state. Okay, so this is all rather abstract, so let's think in terms of the Hamiltonian again, right? So if we look at the Hamiltonian, this is a 2x2 matrix in our case, right? And remember that there were eigenstates phi plus and phi minus associated with this Hamiltonian. And so you can check that you can write this as 1/2 times the projection, 1/2 times the projection onto the upper eigenspace, times by, well, plus this. Okay? So this P phi plus is the projection onto phi plus, and this is the projection onto phi minus. Okay, so you can write the Hamiltonian like this. Okay, so you can check this. If you evaluate H on the basis, then you're going to get, well, you're going to get what you expect. And then a linear transformation is fully determined by its action on a basis. So this is why this works. So let's say that my state has a density matrix M. Okay, then we can talk about the expectation of the Hamiltonian. In other words, we can talk about the value of energy, right? The expected value of energy of our system, right? Well, from probability theory, this is going to be the probability that the system is in the upper end, so that we're in the upper energy state, okay, times by the value of energy, which is 1/2 in this case, okay, plus the value of energy, which is 1/2 times P minus, okay. But on the other hand, if we take this trace formula and we expand it out, we get this. And so this suggests to us that if we know the density matrix of our system, then we know the associated probabilities. Okay? So this right here is the probability that you'll be in the upper energy level, and this is the probability that you'll be in the lower energy level. In fact, this is exactly what we need, because remember, at the end of the day, our problem was to figure out the probability of transition, right? So we had some wobbling happening, and then it died back down, right? And, well, to figure out what the probability is that the electron has jumped down by time t, you just need to compute this quantity right here. Okay, suppose that our system is in a state given by this density matrix right here, pi of t. Now, as with all density matrices, the trace is equal to 1. So that means that we can write pi of t as a linear combination of the Pauli matrices. Okay, so the Pauli matrices right here, sigma x, sigma y, sigma z, they form a basis for C2. Okay, they give us a convenient basis for C2, and they all have zero trace. And so at each moment of time, they're going to be coefficients. They're going to be coefficients x, y, and z, which all depend in time. Now these all have zero trace. We want pi to have trace of 1, so that means that we have to add the identity, and we multiply this entire thing by a half to get the trace right. Okay? So now the question is the following. So we can write pi like this, and notice that x, y, and z are going to be now real for all time. They're real functions. So this means that to specify the density matrix fully, all you need are these three numbers. Okay? Now, furthermore, we've also got this condition that pi squared must be equal to pi. Okay? That's because we're assuming that we can represent our system by a wave function, and if our wave function is psi, then pi of t would turn out to just be the projection onto psi, the orthogonal projection onto this unit complex vector in C2. Okay? Now, if you write this down, if you write this equation down and you work through it, you'll find that this must be obeyed. So rather excitingly, what this tells us is that you can simply describe your system by the density matrix, which you can then describe by simply these three functions, and that gives us a path in R3. And then finally, because of this, that tells us that the path must actually be constrained to the unit sphere. So to summarize, traditionally we describe the system of an electron in the two energy levels by a wave function given by this. Instead, describe it by a matrix known as the density matrix. And our discovery was that you can describe a density matrix at a given moment in time by a point in three-dimensional space. So each moment of time you get a different point in R3, and that traces out a path, maybe something like that. But then because of the pi squared equals pi condition, the path is constrained on the sphere center 0, 0, 0 with radius 1. Now, let's go back to this statement right here. So if the wave function is psi of t, then the density matrix will be the projection onto this wave function. Now suppose that our wave function is phi plus. So suppose that our electron is happily sitting in the upper energy level with 100% chance. Okay, so with a probability of 1. Well, that means that the wave function, that means that the density matrix is the projection onto phi plus. Okay, and we just call that p plus. Now, likewise, if our wave function is phi minus, then our electron is sitting in the lower energy level. Pi of t is equal to the projection onto phi minus. Okay, and these depend on time as well. Now, let's write these matrices in the adiabatic basis. Okay, so I choose phi minus and phi plus to be my basis for C2. Okay, for C2, my basis I'm choosing to be phi minus and phi plus at each frozen moment of time. Okay, well then, that would give me that P plus is 1, 0, 0, 0, and P minus is 0, 0, 0, 1. And so, we can now view these extreme scenarios of the electrons sitting in the upper energy level and the lower energy level by these density matrices. Okay, so following the structure of what we did before, it's useful to now talk about how we'd represent the electron sitting in the upper energy level and how we'd represent the electron sitting in the lower energy level. So again, as a wave function, psi would be equal to phi plus. The density matrix pi of t would just be 1, 0, 0, 0. Of course, this is written in the adiabatic basis. Now the question is, what would x of t, y of t, and z of t be? Okay, so what point in R3, or rather what path in R3 would represent this scenario right here, the electron sitting in the upper energy level with a probability of 1? Well, that takes a little bit of working out, so let's do this. So so pi of t is equal to a half I plus x sigma x plus y sigma y plus z sigma z. And the definition of the Pauli matrices, I should have really written this before. It's 0, 1, 1, 0, 0 minus I, 0, and 1, 0, 0, minus 1. Notice that the trace of all of these guys are 0 and that they are Hermitian. So if I were to write this all out, pi of t would be a half times by 1 plus z, 1 minus z here, x minus iy, and x plus iy. Notice that this pi is indeed Hermitian, right? It's not symmetric, right? But it's Hermitian. So if you take the transpose and then the complex conjugate, you get back what you started, what you had in the beginning. Okay, so now the question is, how would I write this density matrix 1, 0, 0, 0 in terms of x, y, and z? What would x and y and z be equal to? Well, let's just set this equal to 1, 0, 0, 0. And from this, we get that x must equal y must equal 0. Okay? And also we get that z must be equal to 1. Okay? So this tells us that simply the north pole of the unit sphere gives us this particular scenario. And if you do a similar calculation, you'll find the north pole, the south pole of the unit sphere will give us this particular scenario. So to summarize, we have now 4 different ways of seeing the same thing. So we can represent the electron sitting in the upper energy level by either this wave function, which is phi plus, this density matrix, which should be 1, 0, 0, 0, or by the north pole. And then similarly for the lower one. Again, this should be 0, 0, 0, 1. Okay. So now the question is, right, that's all well and good, Sean, but how do you figure out what this pi of t actually is? So we need to set up the problem just like how we did with the Schrödinger equation. So with the Schrödinger equation, and in fact even in classical mechanics, you're given an initial condition, right? In this case it would be, in this case the initial condition is psi at minus infinity is exactly phi plus minus infinity. So psi tends to phi plus as t goes to minus infinity. And then you try and solve this, okay, with the Hamiltonian that was given. Instead, with the density matrices, we want pi of t to tend to p plus as t goes to minus infinity. And we want, and we'd obtain this. And this right-hand side just means HA pi minus pi HA, where HA is the Hamiltonian, but we write it in the adiabatic basis. So it's got that off-diagonal terms. So in fact, we can see, so we can also write HA in terms of the Pauli matrices, and we get a half into sigma z minus epsilon theta dot sigma y. And so if we expand this out and we use pi is equal to a half I x sigma x plus y sigma y plus z sigma z, then we will be able to derive a bunch of differential equations for x, y, and z. So if you work through this algebra, you will derive epsilon x dot is equal to y minus theta dot times z, epsilon y dot is equal to x, and z is equal to theta, z dot is equal to theta dot x, where the dots indicate derivative with respect to time. So this is the differential equation that replaces this and this, okay? Okay, what is the initial condition? Well, we've argued that that would be x, y, and z goes to 0, 0, 1 as t goes to minus infinity. And again, since we're in the scattering regime, we can really just take t to start off with just a really negative value, okay? And because x, y, and z are constrained to the unit sphere, what we're going to get is we're going to get paths on the unit sphere that will start from the North Pole, okay? And they will, well, they're going to spiral because essentially if you divide by epsilon and then send it to 0, you can sort of see that the solutions will be sort of sine and cosine for x and y, right? And that's actually an interesting, something interesting to see, right? Sort of how the rate at which it spirals is going to be related to roughly, you know, your epsilon value. So what we did is we used MATLAB to plot the results for x, y, and z and numerically solve it. So this is one of the plots we obtain. Okay, so different values of epsilon give different trajectories. So notice as epsilon gets smaller, we get tighter and tighter around the North Pole. Okay, this is actually sort of expected because it turns out that the probability of transitioning is 1 minus z divided by 2. And I'll derive that in a second. So because of that fact, it's sort of consistent with the idea that as epsilon goes to 0, the transition probability should also go to 0. So for epsilon is equal to 1, we start at the North Pole, we spiral, and then we sort of end back up here. Okay? And then as we get smaller, we get tighter, like that, around the North Pole. Okay, so the question is, how do you actually compute the probability? I alluded to this earlier, right? I said that it's going to be the trace of P minus times by the density matrix, okay? That would be the probability that you would have transitioned by time t, okay? So this would be pi of t, okay? Now we can explicitly compute this. So this trace doesn't depend on which basis you write your matrices out in, of course. So let's choose the adiabatic basis. So we're going to get trace of, so this guy is going to be 1, 0, no, it's going to be 0, 0, 0, 1. And then this is going to be 1 minus z by 2, okay? X minus iy, x plus iy. 1 minus z by 2, and this is a plus. And if you work through this, you'll get the answer a half 1 minus z, which is very remarkable, right? There's a rather simple formula. If you were able to solve this, then in principle you'd have the probability exactly. So this sort of is kind of promising. And the way you can interpret this is you just have to look at the height of the trajectories of the graph, right? You look at the height and you take the average between it and the North Pole. So the midway point between the point you are on the sphere and the North Pole, that will be exactly your probability, which is why smaller values of epsilon should be closer to the North Pole. With the help of MATLAB, we plotted the transition probability as a function of time. Notice that there is indeed a spike at around t equals 0. And the smaller epsilon is, the smaller the probability is of transitioning. Okay? And notice also that the probability is actually just above 0 for positive time. That's known as the asymptotic probability. And we were interested in plotting this against epsilon. Now what's significant about this is that if you then plot the logarithm against the logarithm, you get a straight line. Right? You get the points tending to a straight line as epsilon goes to 0. Now the literature predicts this would happen, essentially. It tells you that the asymptotic probability should be on the order of epsilon to the n. So it was quite exciting to get this. And we used actually a different function from the one that I talked about before, because we want to ensure that the decay happens quite fast. Okay, we want it to happen faster than 1 over t squared. So we took something like 1 over the hyperbolic cosine. Okay, but anyway, we got the same exact results, which is quite exciting. To sort of finish off, I just want to give a more in-depth comparison to what is in the literature so far, namely what we've read from Betz and Teufel's paper in comparison to what we did. So just to define one more object, we define the unitary propagator to simply be the linear map that takes psi evaluated at s and spits out psi evaluated at t. Okay, so it takes a wave function and it evolves it forward to time t, right? You sort of skip from s to time t. Then, of course, you can derive a Schrödinger equation for this operator, right, for k. Okay, I should have, so that don't worry too much about the superscript and the subscript. And also you can relate this k in terms of pi as well. Okay. Now, in the paper they state that, well, they define this as the transition amplitude, and that's the probability of the electron falling down. It's given by this. And essentially what they say is that this is of the order of epsilon to the n for any n, okay? And also, in fact, if theta is analytic, it can be shown that this is in fact the exponential of minus c over epsilon, which is even stronger. Now, notice, by the way, that, okay, so let's unpack what this means, because it's actually rather subtle. What this is saying is that there are constants Cn such that this is true. So the point is that this Cn need not go to 0 as n goes to infinity. Right? So even as we make n go to infinity, for small epsilon, this indeed does go to 0, right? And it goes to 0 quite fast. However, if we fix an epsilon and we make n go to infinity, this right-hand side might go to infinity. Okay? By the way, whenever you write something like this down, you should say what limit you're considering. So this is in the limit as epsilon goes to 0. So this is true for sufficiently small epsilon. Now, the fact that this right-hand side might diverge means that, so essentially, what you do is you try and approximate this amplitude with a series in powers of epsilon. However, that series does not have to converge. Okay, it might diverge, which means that to get the closest possible answer, you have to truncate the series. Okay, so this is an idea from a branch of maths called asymptotic analysis, and it's got useful applications here. So in the previous literature, that's exactly what they do. They try and optimally truncate the asymptotic expansion in the powers of epsilon. However, in Betz and Teufel, what they do instead is that they notice, or this also goes back to Berry as well in the 90s, so this isn't completely new, but the idea is that the reason why you can get a much better approximation, a much better bound, is that you can try and work out these probabilities in the adiabatic basis, and that's a first step because it controls the off-diagonal terms. They're rather small. However, you want to then switch to a new basis, okay, so that this is, for instance, epsilon squared, so this is even smaller. And so in succession, you get these off-diagonal terms even smaller and smaller, and so you try and approximately diagonalize this Hamiltonian. And this sequence of basis that you need, that you use, is called the superadiabatic basis. And in TOEFL, they're quite BETS and TOEFL, they are rather interested in constructing the sequence of transformations that make the off-diagonal term smaller and smaller. And I'll talk about this very briefly. Okay? So what they do is that they first define time-dependent matrices with the superscript n that have these properties. Okay? And then they define the approximations where pi, k, they're matrices, and you've got epsilon to the k. And you define them like this. And then what they do is that there is this proposition 2, I believe, in the paper, where if x, y, and z are specific matrices, and they happen to be sort of closely related to the Pauli matrices, then pi n is actually equal to, so each of these pi n's are equal to xn, x plus y, and y plus z and z, where the coefficients obey this set of ODEs. Now, does any of this sound familiar? Well, if you were to, quote-unquote, take a limit and make the right-hand side go to 0, then you would exactly get the equations for pi, for the density matrix of the system. So in some sense, these pi n's approximate the density matrix. However, what we wanted to do was to show that this is an asymptotic expansion. Okay? And secondly, notice this was their ODEs for x and y and zn. There seems to be some sort of relationship between the two. Okay, and so sort of carrying this on, you'd probably try and compare what their xn, y, and zn are to our x, y, and z. So just to summarize, well, just to finish off, where could one go here with this research? Well, I would definitely be interested in trying to explore this differential equation even more. And there are loads of interesting and very exciting tools that one can use. As I said, you can use asymptotic, you can use asymptotic analysis, but also you can, try and use, so in the literature it suggests that you might try and use some sort of Laplace transform, or you might use ideas to do with Stokes lines and all of that. So some really, really beautiful complex analysis can come in. And this part of this comes from the fact that if we look at the theta prime that's used, it's a function, and you can imagine t being complex, and so you'd get singularities at t equals plus or minus ITC. And these singularities are basically what cause the transitions to happen. So you can try and do contour integration and all of that, and it's all rather exciting further approaches. All right, well, thank you very much for your attention. I hope I gave some interesting things to think about. Here is a reference for the original paper from BETS and TOEFL, and Sir Michael Berry is also, so I'll write it here, Sir Michael Berry. His work is very important, and his paper in the 90s called, I think it's called Histories of Adiabatic Quantum Transition. This is sort of the basis for this work. So Histories of Adiabatic Quantum Evolution. And if you want further reading, I definitely do recommend the MIT OpenCourseWare on quantum mechanics, especially the third one, taught by Barton Zwiebach. He does a rather nice introduction to the adiabatic theorem in quantum mechanics, and he goes into topics such as Landau-Zener transitions, and if you watch that, it will make everything sort of fall into place, I hope. And he then also even touches on some of Berry's work as well. So if you wish to continue this discussion, and if you have any questions, please feel free to contact me, and I'll be happy to provide some ideas and whatnot. So I'm looking forward to your questions.